take a long time. And this was, so Wednesday we did all just, I answered questions about homework. So we're going back to this example we were working on Monday. What? I don't think we were, I think this is Monday. Yeah. Okay, so we have something like this. Connected by a pin there. There was a 600 Newton force at the pin. I probably numbered those. I would guess I called this member 1, this member 2, and then probably A, B, and C. That seems like the kind of thing I would do. Oh, okay. A was the pin. Oh, called this P because that's what we're trying to find, and this is B. Okay. And we went through Newton's laws for these two things. It's two bodies, two-dimensional problem, so 3 equations per body. And we got this system of equations so far. First equation was, I have them here, and the answer is that those equations are called the exact things I will tell you now. Now I have them. I was just looking at them. Okay. So the first one is 1.03 F12x minus 2. Does this look familiar? 2.81 F12y minus 30 alpha 1. And then what's the constant if you add those all up? Minus 756.3? Yeah. Okay. And then equation 2 says negative F12x minus 10 A2. Why am I doing that one first? So let's go with 0.51 F12x. Oh, yes, got it. Negative F12x minus RC. The order does not matter. It's just a system of equations, so you can put them in any order. But F12x minus RC minus 10 A2x. And that A2 is the acceleration of the center of mass of body 2. And then equation 3 is negative F12y minus 10 A2y is equal to 98.1. And then equation 4 is 0.51 F12x plus 1.41 F12y minus 0.51 RC minus 7.5 alpha 2 is equal to 0. Okay, so there's our system so far. And we have 4 equations. The variables we have are F12, A2, alpha, where are all these equations? Alpha 1, alpha 2, oh, and RC. Oh, that makes sense. Okay, so 2, 4, 5, 6, 7 variables. Okay, so that means we need 7 minus 4 constraint equations. Those are going to come at the joints where that aren't fixed points. Okay, so we're not going to use a constraint at the pin joint connecting body 1 to the wall, but we'll use it at the pin at B and at the pin and slot at P. There's no more Newton's law equations we can derive. That's right. Okay, so at the pin at B, we are going to say that the two bodies, can't fly apart. Pin holds them together. In other words, if this is body 1, and that's B, and this is body 2, and that's B, if we use body 1 to calculate the acceleration of B, and we use body 2 to calculate the acceleration of B, those accelerations have to match. Okay? And then at the pin and slot at P, what do we know about that acceleration? Yeah, look, you're doing the robot. So yeah, that pin can accelerate like this, but it can't accelerate perpendicular to the slot. It can rotate. And actually, that's an acceleration of a point that we're dealing with. Yeah, that pin and slot, the thing, if it was only connected to the pin and slot joint, you could spin it around that pin. And so the acceleration at P can only accelerate parallel to the slot. Okay, so let's first do it at B. This is the most common constraint that you're going to have. So first I'm going to calculate the acceleration of B according to member 1. Then I'm going to calculate it according to member 2. And then I'll set those two equal. So first I'll go acceleration of B according to member 1. Okay. Well, let's think about what member 1 does. That thing just rotates around that pin A, right? This pin A is fixed. And so you can think of that as a circular motion of this point B with A at the center. Okay. Any questions about that? So A is fixed. So B is in circular motion about A. So the acceleration of B is equal to alpha 1 crossed with, I'll call it R1, plus omega 1 cross quantity omega 1 cross R1. And I don't remember what we said about the angular velocities. Did we say this was at rest at this instant? We need those because of this acceleration. Maybe I didn't say. Dang it. I'm going to pretend like I said this before. That has to be given. So we're going to assume that at this instant it doesn't have any angular velocity. It does have angular accelerations. Those are the ones that appear in Newton's laws. And so the acceleration of B, according to member 1, is equal to 0, 0, alpha 1 crossed with a vector that goes from the center of the circular motion to the point we care about. Were these each 3 meters? Is that right? I think that. Okay, so then that vector R is negative 2.82, negative 1.03. And so you get 1.03 alpha 1, negative 2.82 alpha 1, 0. So that's the acceleration of B according to member 1. Okay. And now we're going to calculate the acceleration according to member 2. So acceleration of B according to member 2. Okay, so look at what's happening here. Member 2 doesn't have a fixed point, right? Every point on member 2. So we can't treat this as just a pure circular motion. So how am I going to represent the acceleration of B in terms of member 2? And remember, we want to do it using only variables that have already come up in our 4 equations. Because nope, we don't know that. Nope. So the way we're going to do this is with relative motion. Our 4 equations already have an expression for the center of mass of body 2. So the acceleration of this point B is going to be the acceleration of the center of mass relative to the ground, plus the circular motion, assuming that the center of mass is fixed. So the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. This is a variable that we already have defined. This is A2. And this is circular motion. about the center of mass of 2. So the acceleration of B relative to the center of mass of 2 is equal to alpha 2 cross R2 plus omega 2 cross quantity omega 2 cross R2. And again, it's at rest, so that all goes away. So the acceleration of B relative to the center of mass is equal to 0, 0, alpha 2 crossed with, now we need an R vector that goes from the center of mass of 2 to B. Well, we need, because there's no fixed point, we need to use relative motion. But we could use relative motion with any point on that body. The reason we're using the center of mass is because in our 4 equations we've already defined, we already have the acceleration of the center of mass. That's already something we have to solve for. And so we're going to take advantage of, since we've already used that variable, we can use it in more equations with no more penalty. We don't add any new variables. Yeah, let me just write this equation down. So that's negative 1.41, 0.5, 510. Okay. And if you do that cross product, you get that the acceleration of B, according to member 2, is negative 0.51 alpha 2, negative 1.41 alpha 2, 0. And so now we can set this expression for AB equal to this expression for AB. And we'll just do it component by component, it's a vector equation. So this gives us 2 more equations. Equation 5 star says 1.03 alpha 1. Oh, shoot. No, erase that. So this is the acceleration of B relative to the center of mass. We're not done yet. Acceleration of B relative to the ground is what we want. And that's equal to negative 0.51 alpha 2, negative 1.41 alpha 2, 0, plus A2 x, y, 0. And now we're going to set those 2 expressions equal to each other. So 5 star is 1.03 alpha 1. Yes, that's right. 0.51 alpha 2 minus A2x is equal to 0. And equation 6 star is negative 2.81 alpha 1 plus 1.41 alpha 2 minus A2y is equal to 0. Okay, who has questions about that constraint? We still need one more equation, yep. So these are the two equations that come from the fact that the accelerations at B have to match for those two members. Okay. So now we're going to go to the constraint at P. And the constraint at P is going to say that the acceleration of P, X component, has to be 0. And so I'm going to come up with an expression for AP relative to the ground is equal to the acceleration of P relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. Again, this is what we called A2. This is from circular motion. So the acceleration of P relative to the center of mass of 2 is alpha 2 crossed with this R vector that goes, let's see, how am I going to write this? Goes 2P from the center of mass of 2. That's pretty messy looking, but that'll be clear once I keep going. And then omega 2 cross bunch of stuff, that's all 0 because it's at rest. Okay, so the acceleration of P relative to the center of mass of 2 is equal to 0, 0, alpha 2 crossed with the vector that goes from the center of mass of 2, because that's the center of our circular motion, 2P. So that is 20. Each one's 20 from horizontal. So this is positive 1.41, negative 0.510. And so the cross product is 0.51 alpha 2, 1.41 alpha 2, 0. And then the acceleration of P relative to the ground is equal to 0.51 alpha 2, 1.41 alpha 2 plus A2x A2y. It can't have any horizontal component because the slot is vertical. And so our final constraint equation, 7 star, says 0.51 alpha 2 plus A2x has to be equal to 0. Now we have 7 equations. We know we didn't add any variables in those constraint equations, so we have the same number of variables we had before we started. So 7 equations, 7 variables, and now we can solve. Yeah, because these constraints are equations based on stuff we know about how the joints have to act. And so nothing about how that joint acts gives us information about the y component of that acceleration. That could be 50 or negative 50 or a million or whatever, we don't know. But we do know that the x component of the acceleration has to be 0, because otherwise it would be breaking through that slot.
That's why.
Right. It'd be more complicated if that slot was at an angle, then you'd have to use a unit vector and all this stuff. But yeah, I'd probably do that on the test, yeah. I make it a circular slot. It can't move tangent to the path. Router? Done. Okay. Yeah. As you can see, coming up with problems you can do in a 50-minute exam using linkages can be tricky. Yeah. Okay, so now we have 7 equations, 7 variables, and so I'll set up the matrix. So if you're going to use reduced row echelon form, you need to have 8 columns and 7 rows. Okay, so equations, we have 1, 2, 3, 4, 5, 6, 7. For variables, we have f12, x and y. The order I have it here, I'm going to leave it in the order I have it in my notes. So I'll call this alpha 1, a2x, a2y, rc, alpha 2, and then these are the constants. And so f12x, we have 1.03 of those. f12y, we have negative 2.81 of those. Alpha 1, we have negative 30. And the constant is negative 756.3. All the rest are 0. Equation 2, f12x, we have negative 1. a2x, we have negative 10. C, we have negative 1. Everything else is 0. Equation 3, f12y, we have negative 1. a2y, we have negative 10. And the constant is positive 98.1. Equation 4, f12x, we have 0.51. f12y, we have 1.41. rc, we have negative 0.51. Alpha 2, we have negative 7.5. And zeros. Equation 5, alpha 1, we have 1.03. a2x, we have negative 1. Alpha 2, we have 0.51. And all the rest are zeros. Equation 6, alpha 1, we have negative 2.81. a2y, we have negative 1. Alpha 2, we have 1.41. All the rest are zeros. And then the last equation, a2x, we have 1. Alpha 2, we have 0.51, and all the rest are zeros. And if you calculate all that, use reduced row echelon form, F12, you get negative 143.78, 93.68. A2, you get 16.62, negative 19.18. Alpha 1, you get 11.50. Alpha 2, you get positive 9.31. And RC, you get negative 22.4. So this is newtons squared, radians per second squared, radians per second squared, and RC is newtons. And then you remember what we wanted to calculate? We wanted to calculate the acceleration of p. So now you can go back to this expression that we came up with for the acceleration of p relative to the ground. We only need to calculate the y component because we know the x component is 0. So APY is equal to 0.51 alpha 2 plus A2Y, which is 0.51 times 9.31 minus 19.18. Can someone calculate that? Yeah, I just did that in my head. Yeah, I do reduce row echelon form really well. Negative 14.43 meters per second squared. And so the acceleration of that point P, of that pin at P, is 0x, because we required that, negative 14.43 meters per second squared. And you can use that to figure out, like, you know, like, okay, yeah, that'll cut someone's finger off. So ship it. Any questions about that? Okay, so that's linkages. On Monday, I'll do another example or two, but I'm going to give you some problems with this stuff over the weekend. That's the idea. Okay, have a good weekend. Well, happy St. Patrick's